Alright, so in this video, I'm gonna be talking about this important article about domain adaptation. So this article in 2021. Graph neural network can process graphs of different size, but their ability to generalize across sizes, specifically from small to large graphs, is still not well understood. When do GNNs generalize to graphs of sizes that were not seen during training? In many domains, it is hard to collect ground truth labels for large graphs. For instance, many combinatorial optimization problems can be represented as graph classification problems, but labeling large graphs for training may require solving large and hard optimization problems. In other domains, it's very hard for human annotators to correctly label complex networks. So we identify an important type of data where generalization from small to large graphs is challenging. Graph distributions for which the local structure depends on the graph size. The effect occurs in multiple important graph learning domains, including social biological networks. We first prove that when there is a difference between the local structures, GNNs are not guaranteed to generalize across sizes. There are bad global minima that do well on small graphs but fail on large graphs. We then study the size generalization problem empirically and demonstrate that when there is a discrepancy in local structure, GNNs tend to converge to non-generalizing solutions. Finally, we suggest two approaches for improving size generalization, motivated by our findings. We propose a novel self-supervised learning that aims at learning meaningful representations of local structures that appear in large graphs. So we studied the ability of graph neural networks to generalize from small to large graphs, focusing on graphs in which the local structure depends on the graph size. And the figure shows two graph distributions that differ in size and degree distribution. We show that when the local structures in the test set are different from the local structures in the training set, it is difficult for GNNs to generalize. Additionally, we suggest ways to improve generalization. So D-patterns generalize the notion of node degrees to a D-step neighborhood of a given node, capturing the values of node and its D-step neighbors. So we then prove that even a small discrepancy in the distribution of D-patterns between the test and train distributions may result in way assignments that do not generalize well. Specifically, it implies that when training GNNs on small graphs, there exists bad global minima that fails to generalize to large graphs. We then study empirically the relation between size generalization and D-pattern discrepancy in synthetic graphs, where we control the graph structure and size. We find that D-pattern discrepancy grows. The generalization of GNNs to a new graph deteriorates. So we are given two distributions over graphs P1 and P2 that contain small and large graphs. For example, your source could be a very small graph, but the target domain could be a very large, or vice versa. But in this paper, we focus on distributions that have a high discrepancy. For example, there is a wide domain shift between them. Size generalization is not trivial Before we proceed with our main result, we argue that even for the simple regression task of counting the number of edges in a graph, which is solvable for all graph sizes by one layer GNN, GNNs do not naturally generalize to new sizes. So D patterns are a correct notion for studying the expressivity of GNNs, and D patterns discrepancy implies the existence of a bad global minimum. And we wish to understand theoretically the conditions where the GNN trained on graphs with a small number of nodes can generalize to graphs with a large number of nodes. So we first analyze what information is available to each node after a graph is processed by D-layered GNNs. So this is a definition of D pattern. You see, we define D pattern of a node V recursively. The zero pattern is C sub V. The D pattern is this one. If node V has D minus 1 pattern P sub V. So we see a graph of 4 nodes. Each color represents a different feature. But the bottom is 0, 1, and 2 patterns of the black node. And they have some theorems that any function that can be represented by D-layered GNN is constant on nodes with the same D patterns. So let P1 and P2 be finitely supported distributions of graphs. Let P1 be the distribution of P pattern over P1 and P2D for P2. Assume that any graphs in P2 contain a node with a D pattern in P2 but excluded the P1. Then for any graph regression task solved by GNN with depth 3 but with depth D, there exists a GNN with depth at most D plus 3. That perfectly solves the task on P1 and predicts an answer with arbitrarily large error on graphs from P2.